this presentation, I will be demonstrating my final year project on neural architecture search. When designing neural network architectures, human researchers can be constrained by their prior domain knowledge and creativity. Neural architecture search techniques aim to address this limitation by allowing an algorithm to search through the architecture search space to find the optimal architecture. With this advantage, NAS techniques have found architectures that outperform the best human-designed ones. The following is an overview of how NAS techniques work. Firstly, we have the search space which defines all the possible architectures that the NAS strategy can discover. This includes the number and types of layers, as well as the connection between each layer. As the search space involved can be very large, NAS methods use a variety of search strategies to explore the search space efficiently while balancing between the exploration-exploitation trade-off. For instance, reinforcement learning have been used to explore the search space by letting an agent generate architectures and being rewarded for the performance on the validation set. Finally, different evaluation strategies are used to estimate the performance of a generated architecture on the target data. The most straightforward approach is to simply train the generated architecture on the training dataset and validating its performance on the validation set. Human researchers' domain knowledge can be included into the process by setting up optimization objectives and hyperparameters. Despite its outperformance, NAS techniques have been limited in practical utility by high computational cost. For instance, NAS-NET technique required 2000 GPU days to identify the best architecture in Cypher-10 and ImageNet datasets. This can mean that such techniques are out of reach of many groups. Furthermore, there is a lack of a feedback loop during the NAS process. While NAS techniques minimize human interventions during the search process, it may be prudent for researchers to monitor its progress and determine if the generated architectures are fulfilling the objectives of the search. For example, if researchers can monitor performance during the training process, mistakes made may be identified during the training process itself and allow training to be terminated early instead of waiting for the whole process to be completed before discovering the said mistake. This is especially important in the case of NAS due to its significant computational cost and time required. As such, the objective of this project is to develop techniques that allow NAS to be more accessible for practical use. The key contributions are as follows. An active sampling strategy is to select the most informative samples for training during the evaluation stage of NAS is proposed. By using only a subset of the most informative samples for training during the evaluation process, NAS training time can be reduced. Next, an evaluation dashboard for monitoring and evaluating the performance of neural networks during the training process is developed. This will allow human researchers to understand how well a model is learning the target task while the model is still being trained. Finally, a novel NAS strategy using neural processors is formulated, which will allow us to account for the uncertainty during the search process. In the grand scheme, this project will contribute to the existing literature in various aspects of the NAS process as shown here. I will now discuss the first contribution on the active selection strategy. The primary motivation of this technique is to reduce the cost required in the evaluation process, which is commonly done by training each architecture proposed by the NAS algorithm on the training dataset and validating its performance. However, this involves training each proposed architecture from scratch, which has high computational cost. One way of reducing the training time required is by decreasing the number of training dataset samples and thus steps in each epoch of the model training process. For instance, we can randomly select a subset of the training dataset. However, due to inherent randomness of the selection process, it is possible for a biased training subset to be selected if pure random selection is used. Thus, I propose an approach whereby the most informative samples are selected. The process of active selection is as follows. A reference predictive model is first trained on a randomly selected subset of 25% of the training dataset. The model is then used to predict the class of the remaining training dataset samples, and the topmost informative samples are selected. Informativeness is defined as samples which the classifier is more likely to make an incorrect prediction, which can be measured by the sum of absolute error, where y is the ground truth class label and y hat is the predicted class probabilities. This subset is then used during the evaluation stage of the neural architecture search, together with the previous randomly selected 25% of the dataset. Empirical results demonstrate that on datasets such as NP-NAS, Such a selection strategy enables equivalent performance with just 50% of the dataset used for evaluation. Moving on, a dashboard for monitoring and evaluating the performance of machine learning models during the training process is presented. The primary motivation guiding the development of the dashboard is the idea that evaluating the results of a neural network experiment after it has been completed may be inefficient. For example, if coding errors cause the network to fail to converge, discovering the said mistake after the experiment is run can waste significant time and resources. As such, by developing a dashboard that keeps researchers in the loop during the training process, mistakes can be identified and a deeper understanding of how models converge can be developed. The dashboard's user interface is displayed here. The graph of loss against EPOC is periodically updated in 10-second intervals to allow the user to keep track of the training progress. If the user wishes to visualize the architecture of a particular model checkpoint, they can do so with the drop-down on the top right plane. This feature is expected to be particularly useful for NAS since researchers will now be able to track the kind of architectures produced during the NAS process. Finally, a user may wish to determine how the models perform on test cases. To do so, once the model is selected, an image can be uploaded. The image, its activation map, and predicted class probabilities will be displayed to allow researchers to better understand the models. Finally, a novel algorithm using neural processors for NAS is presented. To identify strategies from the search space, a possible technique is to use a predictive model to predict the performance of each architecture. Neural processors are probabilistic neural networks that aim to combine the flexibility of probabilistic methods with the efficiency of neural networks. Unlike traditional neural networks, neural processors are able to generalize with limited data samples, which is important in neural architecture search as obtaining the data points require training a subset of architectures in the search space, which is expensive. Another advantage is the availability of models uncertainty, which can help guide the search process. The NP-NAS search process is as follows. Firstly, a small number of random architectures are selected from the search space and trained to obtain their validation loss. This will form the initial training set for the neural process. Once the neural process has been trained, candidate architectures are generated by mutating the best performing architectures thus far. Neural process is then used to predict the validation performance. As the number of candidate architectures can be very large, upper confidence bound acquisition function selects the most promising architectures from the evaluation strategy to obtain their actual validation loss. The UCB function accepts both the mean and variance of the regressor, which allows it to balance between selecting the best performing and the most uncertain architectures for evaluation. This is the exploration-exploitation trade-off. This process is repeated until the desired cutoff is reached. The results of NP-NAS are shown here. On the NAS Bench 101 dataset, NP-NAS outperforms the benchmark algorithms, thus showing its efficacy. With that, I have come to the end of this presentation. Thank you.